We're going to start our class with Chapter 2, Analysis of Growth. This is a lesson plan for Chapter 2. In the Section 1, we'll talk about measurements of growth. How fast is it changing? In this section, we'll talk about definition of the function. In Part 2, we'll talk about graphs. Graphs will help us picture growth. In Part 3, we'll talk about misleading graphs. Should I believe my eyes? When one quantity or variable depends on another, the latter is referred to as the independent variable, and the former is referred to as the dependent variable. A function describes how the dependent variable depends on the independent variable. So we can say that independent variable is the input variable, and dependent variable is the output variable. So inside of a function, we're going to input something, and as a result of this function, the computations within the function will get some sort of output. Here's an example. Your height is a function of age. Age is the independent variable, and height is a dependent variable because height depends on age. Another example is the amount of income tax you owe is a function of your taxable income. Taxable income is independent variable, and tax owed is a dependent variable because it depends on your income. Please take a look at this diagram. A function is kind of a box where something is going to be done to the independent variable. On the left side, you have inputs, so something goes inside of a box. Some process inside the box changes the input in some way, and the output is our dependent variable. Let's take a look at an example. The following table shows the most medals won by any country in a given year of the Olympic Winter Games. In the left column we have a year. Middle column contains the number of medals won by a country, and the right column contains the country or a country. What would you label as the independent and the dependent variables for this table? The first thing that we need is a function. What would be our function here? Let's try something. Let's try having country as the independent variable and most medals won by country as the dependent variable. One problem with this is that Germany has several years where it won most medals in the Winter Olympics. In 1992, Germany had 26 medals. In 98, Germany had 29 medals. 2002, 36 medals. In 2006, 29 medals. So in this case, Germany, the input, has 1, 2, 3, 4 output values. In a function, every input value will have exactly 1 output value. Let's try something else. Let the year be the independent variable and most medals won by country the dependent variable. This is our solution. The year is the independent variable and the number of medals won is the dependent variable. Notice that in any given year there's exactly one country that has most medals won. Note, the date cannot be a dependent variable because there were 3 different years in which 29 medals were won. The year does not depend only on the number of medals won. So if we look at the number 29, if this is our independent variable, there's 3 different years that have the same input variable, right? So this is not a function. The year is not a function of the number of medals won, but number of medals won is a function of the year. The percentage change or relative change in the function is a percentage increase in the function from one value of the independent variable to another. The percentage change is calculated using the following formula. Change in the function divided by previous function value times 100%. Example: calculate the percentage change in the US population from 1790 to 1800. Round your answer in the nearest whole number. Here we have the formula that we'll use to calculate the percentage change. The value in the numerator is the change in function. That is the change from 3 and 9300ths million to 5 and 3100ths million. And in the denominator we'll have the previous function value. We have two different function values here. These are the two values. The previous one is 3 and 9300ths. To find the change in the function, we take the difference in the adjacent values of the function for the two function values. And divide by 3.93 million times 100% is 35% change. The following table shows the world population in billions. The first row is the date, and second row is population. This table is very similar to the previous table, except that the data is arranged in rows instead of columns. Part 1. Identify the independent variable and the function, and make a bar graph that displays the data. Part 2. Make a table and a bar graph showing percentage changes between decades. Part 3. Comment on what your graph tells you. Compare the second graph with the corresponding graph for the US population growth. In the first part, we determine the dependent variable and dependent variable. The independent variable is the date. The function is the world population in billions on that date. Next step is for us to find the percentage change in the function. So the percentage change in the world population. To do this, we take the difference in the adjacent values of a population and divide it by the previous value in the population. Right, so for the first one, we take a difference between the population 1960 and 1950 and divide this difference by the population in the previous year, in 1950. Once we do this, the change in the percentage change is 19%. Now we have to do this for every single year, right? So from 1950 to 1960, from 1960 to 1970, 1970 to 1980, 1980 to 1990, and 1990 to 2000. This results in 5 different function values, or the different changes in the function. There's 5 different changes in the function values. And the two graphs are, the first one is the graph, the bar graph for the population, world population. Here on the horizontal axis we have the years. The vertical axis, in the vertical axis we have the population, and the bars represent the size of a population in a given year. In the second graph, we have different changes, right? So different changes in the population. So the first change that we found was the change between 1950 and 1960, and this change was 19%. Right? So here, the horizontal axis, we have the years for which we computed the change, and on the vertical axis, we actually have the percent change. Notice that the world population is steadily increasing. However, the percent change, even though it was increasing at first, the percent change is decreasing. Starting from 1960, the percentage change drops from 22% to 16% per decade. The percentage increase for the world population is still larger than that for the United States. The average growth rate of a function. The average growth rate of a function over an interval is the change in the function divided by the change in the independent variable. This is a definition of the slope. In chapter 3, when we talk about the slope, we're talking about average growth rate. An example: the population of Russia declined from about 146 million in 2000 to about 143 million in 2007. Calculate the average growth rate over this period and explain its meaning. Here the change in the population is negative. If you take the difference in the population 2007 and 2000, this difference is negative 3 million. The change in time is 7 years. We divide those two values and we get negative 3 over 7, or negative 429 thousandths million per year. This means that over an interval, the population declined on average by 429,000 per year.